Okay, it's 10:30, so let's start. This is lecture 3 for CIS6395, and we will finish the networking principle review content in this class. So last time we have introduced the TCP header. Just remember, you don't need to know exactly detail, but you should memorize most part of the TCP header and IP header in your mind, because that's the foundation for any network-based management or network-based security. One student asked a question in the chat is that will we cover any IPv6 in this course? The answer is no, because IPv6, even though it's very mature technology, it's supported by almost all the operating system and software, but it's not widely used, especially in US. It's used widely in some other country, like in some Asian country, because they have very limited IP version 4 resource, and they have so many computers, more than in US. And so in their own country's network, IPv6 is widely used. But in United States, we have a lot of IP version 4 resource because of historic reason. So there's no big urgency to move to IP version 6. So right now, major networks still rely on IP version 4 for networking addressing. So in this course, we will not introduce IP version 6. Okay, so just remember these, the most important part is the flag. Of course, source port, destination port is important for addressing purpose, but most of the bits, if you are a network administrator or security staff, you're dealing with these control bits. Every single one is one single bit. And just remember these bits. We will introduce those bits frequently in the future class. And remember, I told last time, this port number. What's the port number and IP address difference? IP address is addressing of the physical computer, so you can think that that is like a building number in the post office. It's building number. The port number is the process, because in any computer, you are concurrently running many processes. So each networking process running on your computer is assigned with a port number. So that port number is uniquely identifies the running process on a computer, just like a room number in a big apartment building. So for addressing purpose, TCP using this 4 value to uniquely identify a connection. A connection just means a communication channel between one running process on one computer to another running process on another computer. So that's the very rough explanation of this TCP connection. Actually, if you have 2 running process, networking process on the same computer, you can still use TCP for the communication. It's just the source IP address, that the destination IP address is the same IP address, and they distinguish by the port number. And so 2 TCP connections will not be mixed together because they have different value in maybe 1 or 2 of these 4 tuple values. So for a computer to set up a net TCP connection, the operating system need to reserve certain memory in the operating system part. The memory will reserve at least the memory part for these 4 values. Of course, some other related value for the TCP connection. So for networking programming, that's called socket. Like when the operating system create a network connection, the operating system will create a socket. The socket will occupy a certain memory in the operating system, and the socket will dealing with this particular TCP connections. Server host will support many simultaneous TCP sockets, because a web server, for example, a web server may concurrently serve hundreds of client connections to its web server. So for each incoming TCP connection, the web server will create a socket and create a child process to dealing with that particular one connection. So, so each server has upper limit on how many concurrent connections it can serve, depend on the server's CPU and the memory resource. So each socket is identified by its 4-value tuple. And a web server, whenever a web server receives an incoming connection request from a web browser, it will use this fork function to generate a child process. And this child process just dealing with that single TCP connection. And the parent process is still running, listening on the port 80 or port 443 for incoming web browser's client request. So this parent process is always in the listening mode. Whenever there's a connection request, it will generate a child process to deal with that. UDP. So in transport layer, there are mainly two protocols. One is TCP. TCP is the dominant one. Another one is UDP. UDP is a much simpler transport layer protocol than TCP. So you can see this UDP port had a UDP header. So UDP header only has 8 bytes. So only 2 rows here. Source port, destination port, checksum, and length. Length is the number of bytes in this UDP packet. So only have these 4 values. If you compare with this TCP header has 5 rows in this header part. So TCP header is 40 bytes. Remember, each row is 32-bit. That is 4 bytes. So TCP header is 40 bytes. TCP header is 20 bytes for 5 row and 4 bytes each row. So it's 20 bytes. On the other hand, UDP header is only 8 bytes. So UDP header is much shorter, which is convenient for you to send a small packet. If you send a very small data packet, UDP protocol will add less overhead than TCP protocol. Of course, UDP does not provide many other functions in it. We will explain the functions. So UDP header is 88 bytes, and UDP is mainly used for streaming, multimedia streaming applications. So because those applications have different requirements than the data communication. In data communication, we require you to have 100% accuracy. So if you send an email or send a compressed file, if you have one single bit, the whole communication will be corrupted. Then nothing can be recovered. So data communication main requirement is 100% accuracy, but don't have very high requirement on the transmission time. So you can transmit an email in 1 minute, that's still okay. If you transmit a web page in 10 milliseconds or 200 milliseconds, the difference is not that big. However, for the multimedia application, like real-time video, like the Zoom video, it has very high requirement on the real time. Basically, the transmission time need to be like smaller than 200 milliseconds or smaller than 100 milliseconds to make sure that it's real-time interaction. And also, it can tolerate bit error. So for video streaming, if you have some bit error happened in the transmission, the video quality will be degraded, but you can still see the video. So multimedia application has very different requirement. It can tolerate data transmission error, but cannot tolerate delay and the variance of the transmission time. So for those applications, UDP is widely used. Another application for UDP is DNS, domain name system. We will explain that when we introduce DNS in the later slides. So for TCP, remember TCP is the dominant transport layer protocol because all the data-related communication use TCP protocol, like the web, like all these Facebook, Instagram, all those apps, like computer games, all of them is data communication. So they use TCP. TCP is a so-called duplex communication. Duplex communication just means that the two ends, when they talk to each other, they both send data to the other side. They also receive data from the other side. So it's duplex. It's not like walkie-talkie. Walkie-talkie is like when you push the button, you can talk, but you cannot receive. When you release the button, you can receive the voice, but you cannot talk. So walkie-talkie is like a one-way communication. TCP is two-way. So suppose host A and host B, they communicate using TCP protocol. And the host A has byte stream to send to host B. Host B has this byte stream data to send host A. Remember, this is duplex. So each side has data sent to other end. In the network communication, the minimum unit is bytes. So all the data is considered as the byte stream. So, so here we use each bar to represent one single byte. So suppose A and B, they have set up TCP connection. They have talked a little bit. Then at this particular moment, suppose A have finished sending the first 41 bytes, and A next need to send 42 bytes and all the future bytes. And the host B has finished these blue bytes and begin to send 79 bytes to host A. So suppose this is looking at the TCP connection at a particular instance. This is a communication situation. So how does A and B send and receive data to each other? So remember, host A right now is going to send 42 bytes and going on to host B. So suppose host A send a packet. This packet contains 4 bytes data. So suppose this is like a user login and password part. And this data has 4 bytes. And the sequence number, remember TCP header has this sequence number, acknowledge number. I said that sequence number, acknowledge number is accounting by bytes of the data sequence. So the sequence number will be 42. 42 just means that host A tell host B that the first byte in this packet is in the 42th position. So this 42 just means that to tell the other end that what's the position of the current data in this packet. Acknowledge number 79 just means that I acknowledge that I have received from you up to 78 bytes. This acknowledging number just means I'm expecting number 79 bytes from you in the future. So why it's called duplex communication? Because in a single packet, it not only sends data to the other end, it also acknowledges what data I have received from the other end. So it's done at the same time. So this acknowledge number 79 just means what I'm expecting next. And what I have received so far is this number, acknowledge number -1. So that's the data I have received so far. So after host B received this, host B received 4 bytes of data, and the host B will send another packet. Suppose this is a user login username, then host B is the server side password. Server send these 4 bytes. Then this packet will have sequence number 79, because remember, B data, B is going to send 79 bytes for its data section to the host A. So sequence number 79. Acknowledge number is 46, because remember this is 42. Here is 4 bytes. So 42, 43, 44, 45. So that means host B have received 45 bytes from host A. Then the acknowledge number will be 46. Basically tell host A that I'm expecting number 46 bytes in the next data from you. So just to remember how this sequence number acknowledge number is calculated. Then when host A receives these 4 bytes, host A will send, for example, login password, another data to host B. The data is this 7 bytes. The sequence number will be 46. It's corresponding to the previous acknowledged number, because the other side is expecting number 46 bytes. And so the first byte in this data is in the 46 bytes position. Acknowledge number is basically the sequence number plus number of bytes in the previous data packet. Tell host B that I'm expecting number 83 bytes from you in the future communication. So that's how the sequence number, acknowledge number is used in TCP communication. Basically, the sequence number is used when you send, suppose you are one host in this communication. The sequence number, when you send out a packet, the sequence number basically tells the other end that what's the data bytes in my data stream to you. Acknowledge number basically tells the other end what I'm expecting next from you from your data to my side. So that's how the sequence number acknowledge number is used. So you can think that this is a simple login process. You send username, the other side said pass, then you send your password. Okay, any question for this part? Yes.
So if FB was going to have an additional response, it would be like the length of that CIS, how many bits?
You mean what if the next packet from B to A?
Yeah, no, would be like 7 plus 46.
Depend if the host B. So the question is what happened next for the next response packet from host B to host A? The answer is that suppose host B right now don't have any data to send. Then host B only send an acknowledged packet without any single data in it. Then this packet will only have acknowledged number to be meaningful. Sequence number will still be, let me see. Sequence number is 46 is, sequence number will be not used. It only be acknowledged number used. Basically, if I have another line here, it's hard for me to draw. Let me see. My laptop is not touch screen, so if I want to draw a line, it's hard to draw. So suppose this packet come in and suppose there is no data. Then this sequence number will not be meaningful. Basically, you can think that it's empty. Acknowledge number will be data is empty. Then this is acknowledge number is 46 plus 7. It's 46 plus 5, 53. Yeah.
Actual representation, would there be some number in sequence where it would be not used?
There will be some number in sequence, but the receiver will ignore it because there is 0 data in it. So the sequence number can be either the old sequence number or some basically you can use this old sequence number like 79. I don't know exactly what sequence number here, but sequence number is some old number or either plus some value. But this number is ignored by the receiver because this packet has no data. So the sequence number is not really useful. The acknowledge number is used for basically tell the other end that I have received so many data. So the other node A knows that the previous packet has been received successfully by host B. So this packet is called acknowledge packet. Basically, in internet, there are many acknowledge packets, especially for example, for video streaming, for file download or for web page. When the web browser go to some web page, you download a lot of picture, text, but you don't send that many data to the server. But when you receive many packets from the server, for every packet, you still need to send acknowledge packet to the server to tell the server that I have received so what kind of data so far. So for those packets is just like this last one, only has acknowledge number is used to tell the other end what I have received, but data part is 0, it's empty. There's no data. So in internet there are many these kind of small packets. Internet there is one phenomenon is called elephant and mouse. Basically on the internet network, most of the traffic they are in 2 extremes. Either they are very big, basically to the upper limit of the network packet size is about 1500 bytes, or they are very small. These small packet basically like this acknowledge packet or TCP connection setup packet. They basically have header, TCP packet header, IP packet header, but they don't have any data section. So those packets are mouse packet. So internet has this 2 extreme packet format. If data is available as 4 bytes, then something will be like this. Suppose here we have 4 bytes of data, 4 bytes of data. Then this sequence number will be remember this sequence. Host A tell that he's expecting 83. So the first bytes, all this is 4 bytes character C. First byte is 83, 84, 85, 86. So sequence number will be 83. Okay, so suppose we add another packet. The packet has 4 bytes. 4 bytes. The sequence number will be 83 because 83 is the position that you should receive. Remember, host A tell host B that I'm expecting 83 bytes from you. So host B will send data because here the data communication is very smooth. There's no order or packet drop. So host B will send 83 So this first character C is in 83 position. So 83. So see, you can see the rule is that if everything goes smoothly, there's no packet loss, packet error. Then back and forth packet will be like this. The previous packet acknowledge number is next packet sequence number. So basically, you can see this acknowledge number is equal to this sequence number. This sequence number is the previous acknowledge number. This sequence number is previous packet acknowledge number. So that is, it's like a zigzag to go on. And the packet acknowledge number, the current packet acknowledge number is the previous sequence number plus how many bytes in this packet you have received. So that's the basic rule, but you don't need to remember the rule. You just need to remember the concept and know how you add these numbers size of packet into this sequence number acknowledge number. Okay, let me see what's the question. Okay, I answered that question. So if you have 4 bytes here, this is sequence number, basically is copy of previous acknowledge number. Then your acknowledge number is the previous sequence number plus the number of bytes in the previous packet you received. Okay, so that is a TCP duplex communication, how TCP maintain this. And of course, if there is a packet is being dropped, so suppose one packet is dropped, suppose host A, this packet is dropped, host B never received anything. Then host A, the TCP will eventually come out because it doesn't receive any response from other end. The host A will basically retransmit the previous packet to the other end. So there are many ways for TCP to maintain this reliable data transfer. The sequence number, acknowledge number is trying to make sure that each end will understand what the data have been successfully received by the other end. If the data has not been successfully received by the other end, you will do packet retransmission. So you will retransmit the previous packet until you receive the correct acknowledge number. Then you can proceed to go on. So this is a full duplex communication because remember, when you send acknowledgement information to the other end, you also send data to the other end. So that's why this is one packet to go to the other end. You not only send your data to the partner, you also acknowledge what you have received from your partner. So that is the duplex. Okay, for TCP, there is one very important concept is TCP connection setup. So for any TCP connection, before you actually send data, you need to set up the connection. In analogy, it's like you make a telephone call. You always say hello, then the receiver end will also say hello back. So then the caller will know that the receiver can receive your voice, then you can begin to do conversation. For network, TCP connection is like this. Because in the internet, most communication is between client and server. So we use client and server as example. Usually this client send TCP connection request. The TCP connection request is called a SYN packet. It's called SYN packet because this TCP packet has no data. It only has TCP packet header. The TCP packet header, the SYN bit is 1. All the other control bit, they're 0. So this is called a SYN packet. And in this packet, the client also decide what's the initial sequence number. Well, if you see this previous graph, you can think that, well, why not for every TCP connection, we always started from sequence number 0 or sequence number 1, because that's very natural, right? We begin to transmit data to the other end. We always start with sequence number 0 to start. But in reality, you want to use initial random sequence number to start your data communication. The reason is because first, you want to make sure your TCP connection is unique. You don't distinguish mixed with some other things. Another is for security reason. If you choose a random starting point, then attacker don't know how many data, for example, how many data you have sent to the other, or what's the current sequence number or acknowledge number for your communication. So it's harder for attacker to intercept your TCP communication. So for TCP, for the TCP connection request, the client will choose an initial sequence number. So all the data will count from that sequence number to go on. Of course, TCP sequence number is like when it goes to the upper bound, like 2 to 32, that's 4 billion something value. It will go back to 0 and reuse the sequence number. So this sequence number, if it's big, that's still fine, because when you reach the upper limit, it will go back to 0 and restart. When the server receives this TCP SYN request, server will, remember, use fork function to generate a child process. This child process just to deal with this single connection. So this child process will send back a SYNACK packet. This SYNACK packet is using this name because this packet also has no data. The TCP packet header has this SYN bit and ACK bit set as 1. All the other control bit, they are 0. So that's why it's called SYNACK bit. Then the server also choose an initial sequence number for server's data. Remember, the client and server, they both have data to send to other end. So both nodes need to determine their initial sequence number for their own data stream. And acknowledge number field will have client sequence number +1. Basically tell client that I received your sequence number correctly. So this is like challenge and response. So if I challenge a value to you, and if you respond with this value +1, then I know that you have received this number correctly. When client receives this SYNACK, client send another ACK packet. Basically, this packet has ACK bit set as 1. All the other bits, they are 0. And so, and this sequence number is this client sequence number +1. Acknowledge number is a server sequence number +1. This +1 is just for challenge and response purpose. It doesn't mean that there is a 1-bit data in the packet. The packet still has the 0 data in it. But the protocol defined that they need you need to increase the sequence number by 1. So this +1 is just a response. It doesn't mean that one single byte in the data. So after this 3 packet, the client and server, they can begin to send actual data to the other end. So that's why for TCP connection request, it's also called a 3-way handshaking, because there are 3 packets going on before you actually have data communication. So the student asked, when does accept function is called in server side? This question is related to socket programming. If you generate a network program, you want to write your network program, and you do this network function by calling so-called socket API, which is provided by the operating system. Because TCP is supported by operating system. Your network program, your own network program doesn't need to take care of that. So basically, whenever server receive a SYN packet, the accept function running on this server's parent process, because remember, it is always listening on this port 80, port 443 for web service. So the accept function will be activated and accept this incoming connection. If the accept function will generate a child process and to deal with that connection. The server is still running this accept in the forever loop. We're always listening to incoming connection. So all these packets, they are 40 bytes packet because TCP header is 20 bytes. IP packet header is also 20 bytes. I will explain next. So all these packets, when you use like Wireshark to monitor network, you will see that all these packets, they are 40 bytes in size. So this is a TCP connection setup. When you set up a firewall, when you set up router, when you determine like filtering rules, what traffic is allowed, what traffic does not allowed, this TCP connection setup is indicator for you to start to do this checking. So that's why it's very important for you to understand this three handshake. TCP connection closed down is like suppose the client, suppose this client is a web browser. The web browser, when you close a tab or when you close the web browser will first send a FIN packet. FIN packet because this packet has no data. This packet has this FIN bit set as 1. It's one of the control bit. It's called the FIN bit. So this packet sent to the server. Server will send back 2 packets. First packet is ACK packet. The ACK bit is set as 1 to acknowledge that I have received your connection close down request. And the server also send the FIN packet. Then the client send the ACK packet to acknowledge that I have received your FIN packet. So this is a normal TCP connection close down. It involves 4 packets. But for many network programs, they don't want to go through so many hassles. They will simply send a reset packet. Like a client can simply send one single reset packet to the server. The reset packet is a TCP packet that has no data. The reset bit is set as 1. Remember, it's control bit. There are many control bits. This reset bit is one of the control bits. So for the server side, if you receive a reset packet from the client, then you know that the client wants to close the connection. Then you can shut down that child process, release the resource allocated to that socket. And then the client don't do anything after that, just send reset packet, then drop. It's not a polite way to close a connection, because you are not negotiate with each other to make sure, because once you send reset packet, you close your process. But what happens if this reset packet is lost or is damaged during the communication? And then the server will hang on for this for your connection until it time out. Server usually has a longer timeout time for any client connection, so that will waste a lot of resource for the server. So that's why reset is not a polite way to terminate connection. In addition, reset packet could also be exploited by an attacker. Attacker can inject some reset packet in some existing TCP connection. So if it is treated as a normal reset packet, the TCP connection on one end will close the connection. So that could be a security problem. Okay, so that is a TCP connection setup and close down. For UDP, there is no connection setup process. If you want to send the UDP packet to another computer, you directly send it. You don't need to wait for this 3-way handshake, then you send the packet. So UDP is much simpler communication way. Of course, because of that, UDP is not reliable. It's very possible that your packet is lost. Okay, so let's move on to the network layer. It's most important is IP packet header. IP packet header again has 20 bytes, 1, 2, 3, 4, 5 rows. Of course, the packet header could be longer, but this 5 row is mandatory. So the minimum IP packet header is 20 bytes. So this 4 bits is the version. So right now, for IP version 4, it's always 0100. So that's the number 4, the number. And this is the header length. Header length basically tell the receiver how big is this IP header. Because normally IP header is 20 bytes, but some IP packet could have longer header. So this header length will tell the receiver how do you determine what's the end of this IP packet header. These 8 bits, not 8 bits, it's 16, 8 bits. Remember, this version is 4 bits, this header length is 4 bits. Type of service is 8 bits. Type of service right now is rarely used. Basically, all the routers, they ignore this type of service. Because when TCP/IP was designed in like 1970s, when they designed internet, people think that we should support different type of service, give some service more higher priority, some other service lower priority. So when they designed the IP header, they reserved these 8 bits just for that purpose. But later on, they find it's very complicated. If you define different priority for different service, it could be easily abused. And also the routing will also be complicated. Without taking care of the type of service, for every incoming packet, the router just doing first come, first serve. So it's very simple for router. If you consider type of service, router need to consider what's a priority for the packet and move this packet ahead of the queue to transmit out. So that's a lot of service action for the router. So this one is ignored by router right now. No one uses it. The length, this length is number of bytes in the whole IP packet. So this is length is IP packet length. This header length is just the IP packet header size. And the second row, this 42 bits is used fragmentation. I will not explain detail of fragmentation. It's a little bit complicated. When TCP/IP was designed in 1970s, at that time, there are many different local area network. We're using very different physical medium. So some physical medium, they can only support a very small packet, like less than 100 bytes. Some physical medium, they can support packet size several thousand bytes. So at that time, different local area network, their packet size is very different. When you interconnect those local area network together, what happens if you send several thousand packet to another local area network that can only support like 100 bytes of packet? So TCP/IP was designed in this way. When the bigger packet need to send to a network that only supports smaller packet, the bigger packet will be break down into many small chunks. When you break down a bigger packet, this second row will be used to do so-called fragmentation, is to make sure that when you break down the bigger packet, each smaller piece is uniquely identified. This identifier is the ID for this bigger packet. So all the smaller packet, they have the same ID. Then all the smaller packet, they will have the offset in this bigger packet. So you know each smaller piece is in which position of this bigger packet piece. So the host, when the host receive all these small pieces, they know how to assemble them together using the correct order. So that's the usage for this fragmentation. Of course, as time goes on, all these different physical medium for the local area network have begun to consolidate, and many died off because of competition. So right now, only Wi-Fi and Ethernet left. So Wi-Fi and Ethernet, they have similar packet size. It's 1,500 bytes. So that's a maximum byte. So right now, fragmentation is still supported, but it's rarely happen because all the physical medium, they support the same maximum packet size. So fragmentation doesn't use that much anymore. This is time to live. Just determine how many router can this packet go through. Because when every router receive a packet, the router will reduce this time to live value by 1. So when this value drop to 0, router will simply drop this packet. So time to live is still useful because the sender can determine how many hops this packet can go through before it drops. And it also can prevent some wrong routing problem, because if the network has some routing error, some packet can go in this network forever because it can form a loop and move on from one router to another router, form a loop. And the time to live can prevent that some packet live in this network forever. These 8 bits determine what's the upper layer protocol, basically what's the transport layer protocol, whether it's a UDP, whether it's a TCP, or whether it is some other protocol, because upper layer, there could be some other protocol we haven't mentioned, but there could be many upper layer protocols. So this will determine that. This is, again, is the checksum, just like TCP packet checksum. And this 32-bit IP address, source address, and destination address. So that's the IP packet header. How much overhead with each TCP? So basically it's 40 bytes overhead for any TCP-based communication, because 20 bytes of TCP header, 20 bytes of the IP header. So that's the smallest TCP packet on the internet, is 40 bytes. Okay, so that's the IP header information. Then for router to send a packet in the network, every computing device is uniquely identified by IP address. And so IP addressing is an important concept you need to know. For IP version 4, it's a 32 bits of IP address. And we always write this 32 bits into 4 decimal value. So each decimal value basically is 8 bits. So its value is between 0 to 255. So that's the IP address is always between 0 to 255. And you should have a concept that IP address, a computer does not have one unique IP address. The IP address is assigned to the network interface. So for example, my laptop right now is using Wi-Fi. So Wi-Fi interface is assigned with a unique IP address. But if my laptop is also connected with the Ethernet line, suppose I'm connecting both Wi-Fi and Ethernet, then the Ethernet line will also have its unique IP address. Then my computer will have 2 IP addresses. For a router will have much more IP address. If a router has like a 100 Ethernet link or optical fiber link connect to the router, then the router will have 100 IP address, because every interface will have its unique IP address. So here, just to show the Suppose this router has 3 interfaces. Then this 3 network interface will have its own unique IP address. And all the computer connecting to the same interface connect together. It's called a local area network. So all the local area network, they belong to the same subnet. So this is one local area network. This is one local area network. And this is one local area network. How do we define local area network? Local area network just means that all the computers in this single local area network, they can directly communicate with each other without going through a router. They may go through Ethernet switch, Ethernet hub, or Wi-Fi router, but they can directly talk to each other. Basically, they can use, they don't rely on IP address to talk to each other. They rely on data link address, data link layer address, which is called MAC address, to communicate with each other. So that is a local area network. Only when you go through one local area network to another local area network, you need to go through this IP layer, the network layer. You need to go through the routers processing. So in IP addressing using this CIDR protocol basically is classless inter-domain routing. Basically, every subnet is defined by this notation, this 4 decimal value /x, where x is the number of bits in the subnet portion of the address. For example, this is a subnet is called /23 subnet. The 23 just means the first 23 bits are identical for all the computers in this subnet, like in a local area network, or maybe in an organization. All the computers in this organization, if they belong to one single subnet, then they will have all the first 23 bits, the first /x bits to be identical. What they deferred is by the last 32 minus x bits. So that means if the /x, if x is bigger, then the subnet is bigger. If x is smaller, the subnet is smaller. And this subnet, this representation, basically this is IP address when you put all the zero in this host part. So that is IP address to represent this subnet. The ABCD. You can think that ABCD is the first IP address in the subnet, because the first IP address of the subnet is all 0 in the subnet addressing part. The last IP address in the subnet is all these remaining bits is 1111. So that's the last IP address in the subnet. So for ABCD/N subnet, then we know that it has 2 to the power 32 minus N IP address. So when N is bigger, the subnet is smaller. The first IP address in this subnet is ABCD. Remember, as I said, the first address is all the subnet portion is all 0. So that's ABCD. The last IP address in the subnet is when you define this host part to be 1111, then that's the last IP address in the subnet. However, in a subnet, for addressing purpose, usually this first IP address is reserved. No one will use this 0000 as the computer's IP address. This is reserved. In addition, the last IP address is also reserved. It is reserved as a broadcast address. Broadcast address, that means that if you send a packet to that broadcast IP address, basically the last few bits is 1111, Then this packet will be broadcast by the router and also Ethernet switch to every computer in this subnet. So that's called broadcast address. Let's use one simple example to show. Suppose a small organization is assigned with a /28 subnet. Because if you try to use a bigger subnet, you need to pay more fee to the internet organization. We know that one of the address in this subnet is this one. So it asks, what is the first address in this block? What is its subnet representation? So /28 just means the first 28 bits is fixed. The only changeable part is the last 4 bits. So you can first write out the binary representation of this IP address, and then you make the last 4 bits to be 0. You make the last 4 bits to be 0. Then you transfer this back to decimal value. So basically, this is the first address in this subnet. This is basically what change is the last decimal. If you know that the only changeable part is the last decimal, then you don't need to change the first 3 decimals. You don't need to transfer them to the binaries and transfer them back because you know that they will not change for the subnet. So remember, every decimal value here represents 8 bits. So here the subnet only changes the last 4 bits. So that means only the last decimal value for the subnet can be changed. The first 3 decimal value for subnet will always fixed to that value. So this is first IP address, and therefore this subnet representation is the first IP address plus this /28. And how many IP address in this subnet? Basically, it's 2 to power 32 minus 28, basically 2 to power 4. So this subnet has 16 IP address. Of course, the first address, last address, they cannot be used for identification. So only 14 IP address can be used for actual computing device. But the address, the subnet size is 16 address in it. And how do you set your IP address? For a server, for any computing server, you need to set a fixed IP address for your server because you need other people to connect to you. So you have to have a fixed IP address. So for a Windows computer, you set up your IP address using this way, using control panel. In Unix computer, you go to this etc. It has this rc.config. It's system configuration file. You set this IP address. But for the majority of the client, like for us, we are using smartphone, we are using laptop, desktop at home. Then we don't need to take care of this because internet community, they have defined this service, DHCP service. Basically, it is supported by all the Wi-Fi router, by home routers, and whenever your laptop connect to the Wi-Fi, connect to your home broadband cable modem, then this cable modem or Wi-Fi router, it is running this DHCP service. It will dynamically choose an unused IP address in a subnet and assign to your computer. So basically, for the user, you don't need to take care of this. Your computer will be automatically assigned with IP address to use. So that's why it's called plug and play. You plug your computer, then you have IP address. And this is taken care of by the DHCP service. Server assign an available IP address to the client. So that means you connect to the Wi-Fi network, and if you connect to the Wi-Fi network 1 hour later, you may have a different IP address. But of course, all the IP address belong to the subnet used by that Wi-Fi router. And And for IP addressing, it is assigned by this Internet nonprofit organization, ICANN, and ISP actually gets the block of the subnet from this organization, an ISP. So like a Bright House, like AT&T, they get a subnet from this international organization. And the organization is addressing public information. So you can find addressing for all the ISP by yourself by doing Google search. The most important public information is this /8 address allocation. So you can Google search to find the /8 address. I don't know how to do Google search. Okay, so this is IP version 4 address space registry. This page lists all the /8 subnet. /8 is the biggest subnet for internet because the IP version 4 can only support 256 /8 subnet. Remember, this is only the first byte is fixed. All the remaining 3 bytes, they can be changed. So /8 subnet is very big. If you basically you can see how big is the /8 subnet. It's 2 to the power 32 minus 8. So each /8 subnet has 16 million IP address. So that's the biggest subnet. And you can see how the subnet is assigned. This ARIN and this IN, this RIPE NCC. So this is organization take care of the IP address allocation for Europe. So basically every continent has its own address allocation organization. ARIN, I think it's North America. Yeah. So this is ARIN is North America. So basically, it allocates this bigger subnet to this continent-wide organization. Then for the ISP in US, you get your subnet from this organization. But if you see this subnet allocation, you can see that there are some company and organization here, like the Army, Army, because the internet was originally defined by US by the DARPA project. So at the beginning, DARPA project assigned some /8 subnet to some company and also this government organization like Army, like DOD, like the Paralab, and like this Ford. But quickly they find out this is not a good way, because once you release it out to the company, you cannot get it back. And there are only 256 subnets there. So they quickly stop doing that. But for the subnet allocated out, you cannot get it back. And so right now, there are still some companies like Apple has a 16 million subnet, which is a waste of resource because they don't need to use such big subnet. And like a Ford, they don't need to use that. Like a DOD, they actually don't need that big subnet. So all the remaining subnet, they began to allocate to the continent. Then the continent, they allocate to each country and so on. And so once you release out, you cannot get back unless the organization give it back to you. Actually, some organizations, they give back this /8. For example, MIT. If you find this web page like 8 years or 10 years ago, you can see MIT is allocated with 18. I think it's 18. This subnet was allocated to MIT. And a few years, maybe 10 years or 8 years ago, they released back to the organization. So MIT is not using this big subnet anymore. So this is a bigger network allocation situation. And you can find your own IP address by Google search IP address locator. There are many websites can pinpoint what's your IP address. So you Google search IP address lookup location. And there are many websites to show what's your IP address. So here, then you can see what's your IP address. And this IP address is actually global IP address assigned to my laptop by the UCF gateway. If you check your IP address, like in Windows computer, you use ipconfig, you can see that my IP address is actually this one, is 10.38.117, because this is a private subnet. UCF is a very big private subnet within UCF campus network. All the computer is assigned with 10,000 something IP address. But when your traffic goes to the internet, the gateway will temporarily assign a global IP address to your particular computer. Then you can communicate with the internet. That's why my computer's global IP address is this one. So the gateway, UCF network gateway will do this address translation between the private IP address and global IP address. And of course, this IP address is temporarily given to my computer. If I shut down my computer and open it again, my global IP address may be changed to another global IP address belonging to the UCF subnet. UCF, I remember UCF is assigned with the 2/16 subnet. It's 2/16 subnet. So that's about 120,000 IP address within UCF campus network. Okay, any questions so far for this address allocation? Yes.
For DHCP, is there like for those servers, is there like a countdown to when they could like say this we will not reserve this anymore?
Oh yes, the question is about DHCP. Yeah, I didn't explain DHCP protocol in detail. DHCP protocol, like when you open your laptop, your Wi-Fi interface will send a DHCP request to the Wi-Fi router you connect to. The Wi-Fi router will respond to give you one IP address and also tell you what's the lease time. So lease time basically tell you your IP address, you can use it for the next, for example, 1 hour. When the 1 hour time up, your computer need to re-request another IP address. Yeah.
Does that automatically happen every 24 hours?
How much time leased by the DHCP server is depend by the configuration of the DHCP server. So some could give longer time, some could give you shorter time. Yeah. Yes. Yeah, I remember that's the case, but 2/16 subnet just means UCF request the upper ISP with 2/16 subnet. This 2/16 subnet, they are first 2 bytes, they are different. So one subnet has this 132, 170 first 2 bytes value. Another /16 subnet, they have another first 2 byte value. Yeah. Okay, I said, okay, so the student asked what's the book to recommend for networking. As I said in the beginning, the recommended book is this computer networking book. All these slides, I used some slides from this computer networking book. You don't need to buy the newer version. Newer version is expensive. You can buy some very old version, like 4th version, 5th version. Right now, it's a 7th or 8th version for this book. You can buy some very old book, and the basic concept is still the same. When you make UCF slides. Okay, UCF has a 2/16 subnet. Just means UCF has obtained 2/16 subnet from the global internet. So these 2 subnet, they are global IP address. They are not private IP address. So you may wonder what is a global IP address, what is a private IP address. That's a concept I will explain next. Basically, it's called a network address translation protocol, which is a very good invention for the internet, because in the 1970s, at that time, nobody worried about IP address resource. Thinks that IP version 4 have 2 to the power 32 bits, 2 to the power 32 IP address, which is 4 billion IP address. So at that time, they think this is unlimited resource. But quickly they find out that this is not. And so internet community developed a new protocol called network address translation protocol. Basically, in one, for example, one good example is a home Wi-Fi router. So you can think that this is a home Wi-Fi router. The home Wi-Fi router is assigned with a single IP address by your broadband provider, like by Bright House or AT&T. They assign a single global IP address to your home Wi-Fi router. But in your home, you could have 5 or 10 or even more computing device, like laptop, desktop, iPad, smartphone. So how can you go to the internet at the same time? So all the home devices, they are assigned with a private IP address. And the Wi-Fi router has one single global IP address. So this Wi-Fi router will run this NAT protocol, network address translation protocol, to basically modify the IP address when the packet come in or when the packet come out of the local area network. So the basic way is that this Wi-Fi router will have a so-called NAT translation table. It's a very simple dynamic table maintained by the Wi-Fi router. Whenever then the internal computer have private IP address, so they cannot be connected by the outside internet computer. Only internal computer can connect out. So that means your browser can connect to the server in the internet, but internet server cannot connect to your computer directly, because your computer has private IP address. And so suppose your computer here send a web request. This is a port 80. So you are connecting, send a TCP SYN packet, SYN request to an outside server. The outside server has this IP address. Your computer has this private IP address. And this is a source port and the destination IP address, that's destination port. So when this packet goes to the Wi-Fi router, the Wi-Fi router will change the source IP address and source port. When the Wi-Fi router changes this, Wi-Fi router will keep this entry in its translation table. Basically say that I change the port from this port to this one. I change the IP address from 10 to this global IP address of the Wi-Fi router. So that's why it's called network address translation. It changes the address as a packet. So when this packet goes to the web server, web server will respond with a SYNACC packet. So the web server, the destination IP address is this global IP address, and this port is corresponding to the source port. When the router receives this packet, the router will check this lookup table to find this entry, then translate it back with this destination IP address and the destination port. So it will translate back with this private IP address and the original port number. Then this packet will deliver to this source client computer. So in this way, it can maintain this TCP connection, but the IP address and port number will be changed on the fly when the packet goes through this Wi-Fi router. So that's how this Wi-Fi router can maintain multiple TCP connections by using a single global IP address. All these computers, their outgoing traffic for the internet side, it looks like they all come from a single IP address. They all come from a single computer, but actually it's 10 computers behind it, sending all the packet to the internet. Okay, I think time's up. Time's up. Oh, okay. I think the students showed a free link to the book. And anyway, you can look that. Okay, that's all for this class. Let me stop sharing. And see you this Monday. I still have 10 slides. I need to finish it next class. Yes. See you next time.